Thanks, Heike, and welcome to everyone. Good morning, good evening. Thanks for joining us at various times around the world. So my name is Albert Fisher. I'm director of the WMO Integrated Global Observing System Division here in the WMO Secretariat, and it's my pleasure to welcome you to this workshop. Water, along with weather and climate, are of course key goals, key output areas and areas of work for WMO, for WIGOS. And water is pervasive in nearly every aspect of human safety, our well-being, economic activity. Floods and droughts, water supplies, agriculture, energy production, ecosystem health, the hydrological information can underpin decision-making in each of these areas. And as climate variability and change intensify the global water cycle, the importance of timely and reliable hydrological observations is really growing. So ground-based hydrological observations have many challenges related to data sharing, and some of that is overcome from satellite observations. So I'm really looking forward to this workshop, which brings together practitioners from the satellite provision side, from the service delivery side in hydrological services, to talk about core and recommended satellite data for hydrological applications, and to work on their inclusion in the WIGOS and WMO regulatory frameworks for core and recommended data using the WMO Universal Data Policy. So again, welcome very much. Thanks for your participation. I'm really looking forward to the results of this important workshop. Thanks a lot. I'll hand over to Fiona now.
Thanks, Albert. And I guess I'm also just going to say thank you to everybody for participating. For those of you who don't know me, I am the chair of the expert team in space systems and utilization. And together with the task team on Earth HydroNet, we are undertaking this activity to define the core satellite data for hydrology. Hydrology is the third application that we have been defining the core satellite data. We started with global numerical weather prediction, and we've done nowcasting, and now we're doing hydrology. As Albert said, the purpose of this is to define core and recommended satellite data so that operators and producers of data can understand that these are the observations that we really need to deliver our services. So as users, it's very important for us that our applications accurately list what is needed to deliver our services, because the WMO Unified Data Policy will say that core data must be shared freely to everybody, and recommended data is recommended to be also shared freely to everybody. So what we're doing here today is we've brought together users and satellite data providers, and the idea is that by the end of this workshop, we will have an agreed list of what are the core satellite data requirements to deliver hydrological services. And we really appreciate every single one of you who has put in your time to come to this workshop, and who will help us to make sure that we have a really good list that will enable us to deliver our services into the future. I'd really like to thank Li-Hang Zhou, who is the vice chair of the ETSSU, and we'll be handing over to her soon to say more about this. But Li-Hang has really led this activity, and we wouldn't be here without all of the hard work that she has put in with the task team on Earth HydroNet. So thank you, everybody. I'm going to be a bit quiet tonight because for one reason or another, I have a lot of sleeping people nearby me, and it's quite late at night in Australia, but I'll be listening in, and hopefully you'll all be able to contribute to this workshop, and then we'll have an efficient process, and we'll get to the end tomorrow, and then we'll be good to go with recommending this to our parent bodies and up to INFCOM. Thank you.
Thank you so much, Fiona. We also appreciate your efforts on this activity and for core data overall as a co-chair of ETSSU. So thanks a lot. Also, as said, I hand over to Li-Hang, who is actually now introducing the workshop agenda and the goals, so we can review the agenda a little bit. So over to you, Li-Hang.
Thank you. Thank you, Fiona and Albert, for excellent introduction. My name is Li Hangzhou from NOAA and Vice Chair for the ETSSU. And I joined Albert and Fiona. Welcome to the virtual WMO workshop on the core satellite data for hydrology. And this is important two-day event. So our primary objective is to establish a list of core and recommended satellite data to support hydrology application areas. Now let's start reviewing our agenda. The workshop agenda is split into 2 days. So day one today covers introduction and then WMO data policy, and followed by a session dedicated to the satellite data requirement for hydrology, featuring 10 to 15 minutes use case presentations from global regions, from Pacific to Asia, and then data simulation by Sujay from NASA. And then we move to the Africa, Europe, South America, and North America, and with polar region use case presentations. And and day two, tomorrow, we will focus on the actual core satellite data, including parallel breakout sessions for user requirement, and for those breakout sessions, we're going to discuss 5 questions that already on the link there on the meeting web page, and including any discussions about the core satellite data list, and then followed by discussion to agree on the list of the core and recommended satellite, and to achieve our objective of this meeting, to establish a agreed list of core and recommended satellite data to support hydrology applications. So just want to remind everyone, well, this is a workshop we're going to target to have a agreed list. We still, after the workshop, we still have a opportunity to go back and forth and incorporate any final comments into our final version. With that, I'm going to turn back to Heki for WMO policy introduction.
Thank you so much, Lihang, for your kind introduction of the agenda. So that's exactly how Lihang explained. So the next, I'm going to talk about the WMO data policy a little bit more detailed. I can share my screen and slides from here. Do you see my screen now?
Yes.
Yes.
Okay, good. So I'm going to talk about in this presentation about the overall efforts, how WMO has been approaching this core and recommended satellite data establishment, and status of few applications, and then of course hydrology, which Lihang is then actually going to present more detailed in the next presentation. So first, overall, about the little bit about the WMO data policy, and then I will cover a few applications which are already defined NWP and nowcasting, and then hydrology, and then I will talk about a little bit about the timeline. So this goes back to a few years. 2021, WMO renewed its data policy. So the resolution 1 WMO unified data policy was approved, and this was replacing the old resolution which were defined application for the different applications. So there used to be resolutions for weather, hydrology, and climate, but now there is only one resolution covering all these applications. And there are now two main categories of the data. So there is core and recommended, and core is data which shall be exchanged by WMO members, and recommended is should be exchanged. So that's recommended. The policy is addressed to national governments of WMO members, and we cannot dictate the private sector entities. However, the exchange of core data is considered mandatory irrespective of data origin, which is a little bit, of course, kind of challenging thing there when we come to the private sector data used by the WMO members. What is there in the data policy related to space-based observations? For example, it says there that the satellite data required in order to ensure the performance and quality of NWP output as agreed by WMO members, satellites, and relevant satellite operators, as listed in the WIGOS manual. And also in the item B 112B, it says that we shall share the required data to support nowcasting application, including the generating warnings and advisory products. And again, it refers to the manual and WIGOS. So as you see in the resolution document itself, it's very high level, and then it refers to WIGOS manual for the details. And same thing for hydrology, it's exactly like this. So it requests to share the data for the satellite data for the operational services, and then it refers to the WIGOS manual. And this is why we are here. We want to define in the WIGOS manual that which are those data sets where this resolution is actually referring to. We have started this effort already some years ago, and we have first in the WMO Secretariat, we have provided an analysis of the space-based observation capabilities, especially among the CTMS members, but also in CEOs, and it has been effort together with ETSSU, of course, and ED Space Weather and the CTMS Space Weather Coordination Group. And we have been using WMO Oscar Space, and then it takes into account WIGOS Vision, and then there was this NWP position paper, which was already created by the previous expert teams, which is actually kind of the foundation of the NWP core data. And the document, we were documenting the current core measurement capabilities of the CGMS members related to GEO and LEO measurements and space weather. Then we had a round of bilateral discussions between the satellite operators and WMO, that how they see this and what kind of approach they want. And it was very much requested by the satellite operators that we really engage with the users, and this is one of the reasons we are here in the workshop as well. So there has been lots of work before this workshop, and we have been engaging with the users a lot, and this is kind of the where we then want to summarize our efforts before this workshop. And 23 we organized this workshop for the NWP, similarly like now. And then Infcom 3 approved this core satellite for NWP, and then it was also approved by Executive Council in 24. And this is how it is. So these are the lists which are there for the NWP now already approved in the WIGOS manual, and there are links in the presentation. You can go and see. And I don't go into the details, but this is what we showed. So how we present. So we have a type of satellite sensor, then we have products, what we request, level 1 and also level 2, and then we have an attributes column, which is the idea there was that if there are any further details we want to say, the data which is going to be assigned as core. As you see, for example, hyperspectral infrared sounder, there is an attribute that we don't expect the entire radiances to be available because it's a huge effort for the satellite operators to put entire dataset available. So that's why we have defined that compressed data with, for example, principal components is enough there. So these kind of details we give in the attribute column there. And then we followed from there. We continued with nowcasting application. We had a similar process there. So there was the ETS SSU task team to consolidate the experts view for nowcasting core and recommended data. Again, we defined this draft table of what is requested on top of NWP for nowcasting. And this work is currently ongoing and extends to nowcasting application. We have had similar workshop last autumn for nowcasting, so it's now in the final draft status and going to be then approved in the INTCOM for later this year. And then there we continued for hydrology, which is a very topic for this workshop. And there we have been working together with ETSSU and the task team of Earth HydroNet. And first of all, there has been nice combination of work, not only satellite data, but also the in situ and the very much also for the hydrological variables which should be measured. And this has been nice combination of work on space-based observations and the surface-based observation side. And as we know, some variables require a combination of ground and space-based observations as well as model data. And then also the issue there is that many of the hydrology measurements they still rely on R&D satellite missions, and of course not all variables listed by hydrological variables can be detected from or measured from space. So here we are now in the workshop for the final user engagement. And the idea is that we prepare the workshop statement as an outcome from this workshop together with these tables of core and recommended data. And also we have recognized and together independent from this effort that there is also some guidance of hydrology network design document which needs some more work to be prepared. So there is more than that, more than core recommended data for hydrology, which needs to be documented in the WICOS manual as well and WICOS guide. Just to remind you that as we define this now application by application. However, for the user and especially for the satellite operator, it's they want to know that what are the altogether the core satellite data they should have available for the user. So at the end of the day, we have this kind of one table approach where we don't have like in the WICOS manual different tables for different applications. So this is how we do it. Of course, we want to monitor which requirement is coming for which application. But in the WICOS manual, it's enough to have this kind of one table approach which is clear for the satellite operators that these are the data sets they shall have available for the WMO members. Then just a final slide about the timeline. So the target is INFCOM 4 meeting end of November this year, where we seek approval for these amendments in the WICOS manual. And as you see there, the final draft should be available like Q2 already. So we don't have too much time when we need to submit actually the final document to INFCOM 4. So there is still some time after the workshop, but not too much. So we can still have some coordination with user community and satellite operators, but pretty much we are there. And I'm confident we will find a final draft from this. We have been working so hard for this already, so I'm pretty convinced on that. So that's my presentation. Thank you very much. And if there are any questions, I'm here. Thank you so much. Any questions? If no questions, then let's move on. We start with session 1 now, which is about the satellite data requirements for hydrology. And the first presentation is by Li Hangzhou, introduction to WMO core satellite data for hydrology. So over to you, Li Hang.
Thank you, Heikki, for excellent introduction of the WMO data policy and general background for the core and recommended data development. So now let's focus back to the hydrology core and recommended data sets. So first, the definition and scope of the hydrology applications. Really, we focus on monitoring and predicting the water cycle, supporting the water resource and hazard warnings. And the scope covers really the key Earth system components, including surface water, subsurface water, and the cryosphere ice and snow components. So as mentioned, the satellite data provide vital spatial distributed global observations and regional observations, especially in areas lacking in situ measurements. And the core data table are designed to support the critical hydrology applications such as flood forecasting and drought monitoring and water resource assessment. Thanks, please. Just a snapshot of all the process and the key work activities bring us here to develop the core and satellite data for hydrology applications. So a lot of progress has been made by cross teams work. Especially the task team Earth HydroNet defined a list of the physical variables required for hydrology applications and compare the tables, include the inputs from the hydrology experts and also the satellite experts. And the ETSSU coordinate the satellite experts' inputs and prepare a draft table of core satellite data sets linking the satellite observations and variables to the for the hydrology applications. And so the team members really work hard on this and together with hydrology experts and our home agencies. So lots of hard work and support there. And then we follow the approach as he mentioned, the NWP and nowcasting to develop this one table approach. And the satellite operators also reviewed the draft table of core satellite data sets and with respect especially to their data policies and provide many very good feedback and input. So let's go to the next. There's also beyond the data, there's also recommended practice for the core hydrology data. So the data share all the core data shared globally in near real time and real time, aligned with the unified data policy, and provide comprehensive documents on instruments and also algorithms and all the relevant aspects. And also, we must plan for sustained long-term data provision to ensure continuity hydrology record, and also provide calibration data with traceable estimates, and maintain and provide unrestricted open access to the satellite data archive and include all the metadata. Next slide, please. Oh, okay. So Ricky, Heikki already showed this. So we're targeting to gain the Infocom for approval toward the end of the November this year. So I believe this is the last slide. I just want to take the opportunity to thank everyone engaged with this activity and contribute to this important work. So now, Zoya, if you can please bring up the table which is on the link of the website as well. So the next few minutes, let's just very quickly go over the current latest version of the table, especially for the focus on the hydrology application. So let's start with the geostationary satellite. For the sensor multispectral with IR imager, start with level 1 radiance, which is fundamental input to hydrology specific applications, and then LST, cloud products, precipitation, water mass, and flood extent, and snow ice cover and extent, as well as land cover, vegetation type. Those are identified as core satellite data supporting hydrology applications. I believe most of the recent comments have been addressed by Zoya, and we will have a the opportunity to discuss more tomorrow, and also email. So I just go through quickly, and let's move on to the hyperspectral infrared sounder on the level 1 imagery, especially for the selective spectral information, as well as vertical temperature moisture profile derived from hyperspectral infrared sounder are identified as core data for hydrology. And then for the next session will be the sun-synchronous core satellite data. So start with the multispectral with IR imager and daylight imager, the level 1 radiance, and level 2 sea surface temperature, including the inland waters like lake and other inland water bodies. Level 2 land surface temperature, cloud products, land cover, vegetation type, LAI, FR, water mass and flood extent, snow cover extent, snow albedo, precipitation, also the chlorophyll turbidity, suspended matter, and reflectance are identified as core for the hydrology applications. So I hope people can read it. Yeah, yeah. And the next session is a hyperspectral IR sounder on the level 2 vertical temperature and moisture profile from the SSO hyperspectral sounder identified as core data. And for microwave sounder, the level 2 total perceivable water, vertical temperature, moisture profiles, the precipitation are all identified as core data supporting hydrology application. And next session is the microwave imager. For that, the level 1 readings and level 2 water surface temperature, the precipitation, soil moisture, root zone, soil moisture, and lake ice cover, snow water equivalent. Oh, sorry, sea ice. Are all identified as, I think, yeah, so identified as a core data. Sorry, I think I think my column is there. Okay, yeah. Sorry about it. So, yeah, sorry, I read it wrong. So, not sea ice, the root zone, soil moisture, lake ice cover, and snow cover, and snow water equivalent. Sorry, yeah. For scatterometer, the soil moisture and root zone soil moisture identified as core data. And move on to the next section, the other LEO satellite data, the storm imagery, total precipitated water, cloud water, and also the vertical temperature and moisture profiles. Are identified as core data. And move on to the there's also water surface temperature, precipitation, soil moisture, and root zone soil moisture. Those are identified as core data from microwave imager and the other LEO. There's also lake ice cover, snow water equivalent snow cover. So they're very consistent with the microwave imager from the LEO satellites. If we can move on to the wide swath radar, the level 2 surface water extent and slope as identified as core data. And the next, go on. Yeah, for the absolute calibrate broadband radiometers and total solar irradiance and solar spectral irradiance radiometer, the terrestrial radiation level 2 data are core data supporting hydrology. And then for the narrowband imager, there's we identified the level 2 chlorophyll turbidity and suspended matter and the reflectance radiances as core data for hydrology. All right, let's move on to the last section. That's recommended data. So for the sun-synchronous satellite missions, the multispectral VISIR imager and data band for that. The level 2 land use changes are identified as core data, as recommended data. Sorry, so as suggested by the by NOAA team, and then move on to the data from other LEO satellite data, the water mass and flood extent from SAR imager identified as recommended data sets. And if we can quickly move on to next page, yeah, there's also river lake ice and snow water equivalent SWE from the SAR identified as recommended data. And there's also added data for hydrology recommended data set, the water surface temperature, the snow cover, and lake ice cover from high resolution optical imager identified as recommended data sets. And then there's also gravity field data and water storage from gravitometer missions identified as recommended data set. And then the LAI and the LAI profile identified as recommended from LiDAR data. Then there's GNSSR data for soil moisture and water mass and flat extent are also recommended data as recommended by the NOAA team. I believe that's the end of the table. I know we went through it very fast, but again, we will have more opportunity to discuss it tomorrow. And with that, I'm afraid I have to turn back to Heikki. We start the next presentation.
Thank you, Li-Hong. Are there any quick questions to Li-Hong before we move on? Go ahead, Marcelo.
Thank you very much. Thank you for the very clear presentation. My point is on the second column, header says product, and we are talking about data here. Are we using them as synonyms? In my understanding, products would refer to higher level products, sorry. Whereas data is more related to lower level satellite observations, right? There's always a model involved in an algorithm involved in transforming from the energy or the electromagnetic domain into an environmental variable, but it seems to me like products like the root zone, soil moisture implies also incorporating some external modeling on top of the satellite data. I don't know if that makes sense to the group, but I feel it's a little bit different things. I don't know what you think.
Yes, I see what you're saying. I completely agree with you that it's a little bit mixing up with the kind of pure data sets and then kind of higher level products, because we have now in the one column we have level 1 and level 2 data, and even in some cases even probably like level 3. And this has been the dialogue we have been actually having when we have preparing this, that where we should kind of limit, especially for the hydrology. There are many data sets requested which are very much relying on third-party data, some model fields, etc. So it has been a little bit like a compromise. If some data sets are really a lot of based on the models, etc., we have left them out. So that we try to kind of follow the data sets which satellite operators can easily provide without relying on other data sets. So it has been a little bit like a compromise. And then also what I want to remind here, that this what we try to provide here is it's an initial list. So I mean, the idea is that it's going to be updated in every INFCOM if there are further updates, and then we have a review cycle. Now the idea is, for example, for the next INFCOM 5 after this year's INFCOM, we want to then already review what is there now for NWP, because things in the NWP modeling, for example, are very much advanced since we have defined that. So the idea is that it's going to be updated. So we should target on initial list, which is then the sufficient for the operational services at the moment.
Thank you very much.
Any other questions? And just to comment that as you see, there are still some comments open. Some of them, they are actually very new comments we still have there. I mean, there are no issues. Basically, we just wanted to leave them there, that the people see that okay, there were new comments still coming into the document, and we have been NOAA especially provided many comments, and we have been in contact with NOAA and find actually good approach that how we take into account those comments Noah provided. Thanks a lot for the nice review by Noah, by the way. So there are a few additional data sets, and then a few things are actually moved to recommended data from core as there was a good justification for that. So that's the very new edits in the document now. I don't know if Noah wants to further discuss on these additions you did, or should we discuss in the breakout rooms? Then maybe tomorrow maybe it's better, so we can move on now.
Suggest we move on.
Okay, let's go to the next presentation then. So now we start very interesting part of the session 1, where we are going to hear about these use cases. And first is satellite-based hydrological applications from Pacific, and I give floor for the Luigi Renzullo from Bureau of Meteorology. So over to you, Luigi.
Thank you. I was wondering if I could share my own slides, if you don't mind, just because
Sure, that would be great.
I did notice a couple of typos, and that would distract me if I focus too much on those. So hello, everyone. Thank you for having me, and it is a great pleasure for me and an honor to present this work on how those of us in Region 5, of which the Bureau of Meteorology and our friends across the ditch, as we like to say, in New Zealand, use satellite Earth observations for hydrologic applications. And I just want to pay special acknowledgement to my Bureau of Meteorology colleagues here on TAN, who we work close together for the last few years to boost Bureau's capability in hydrology from Earth observations. So I just wanted to highlight, so I'll be talking about some present activities, as well as how we might do things better and differently in the future to exploit the wealth of satellite observations, be they the radiance levels right through the value added enhanced user products. So in the end, I just want to remind everyone that the motivation for us to look at Earth observations is ultimately so that the land surface plays well or interacts well, so to speak, with the atmosphere, because in the end, if we don't get the land surface right, the fluxes to the atmosphere, well, could be wrong. And so we really want to look at how best to constrain the land surface for carbon, water, and energy cycles to improve our NWP ultimately. And a useful way I felt to break up how we utilize Earth observations is to think about this level of usage from the soft through to the hard. The soft being levels of utilization that really are about evaluating model performance against independent satellite observations, for example, in which case you might consider anything goes. There's no requirements that the data from satellites be a long time series or even have a longevity decades or what have you. The calibration utilization, for example, puts a little bit more of a stringent quality control on the Earth observations. We might want to use some sensors but not others when we're talking about time series that span multiple sensors, like the AVHRR archive. I know there's a lot of effort gone into harmonizing those time series, but I think generally the idea is that the MODIS is the reference or the highest quality. So having that judicious, careful consideration of what data you'll use, that's what I mean by calibration. It's sort of fits in that middle ground of between soft and hard. And when I talk about hard, I'm thinking the real assimilation, really bring those observations into the physical modelling. And that could be through forcing, like as precipitation, or through shortwave radiation, and maybe even assimilating like soil moisture. In which case, all those things, we really need top quality. We want to make sure there's consistency of the observations through time. We want operational data flows, low latency, and to make sure that these data have a lifetime beyond their 1 or 2 satellite missions. So just an example of verification, so in a soft application to begin with. Siwan Tan and I, we looked at evaluating the model. In this case, it's the Australian Water Resources Assessment Model. Evaluating its root zone soil moisture. So on the left, we've got the direct comparison of model estimates against the network of in situ measurements. And, you know, we all know the pros and cons of in situ observations for things like soil moisture. You have, in this case, maybe 20 observation networks comprised of cosmic ray sensor networks, TDR sensors in the soil profile. Yeah, so you may have about 20 across the country. What we thought is to sort of see how we might be able to evaluate root zone model estimates across a wider range of, wider area. We thought, well, we know that the grassland areas are pretty strongly correlated with soil moisture availability. So we considered the NDVI for grassland areas as perhaps a useful indirect but useful covariate with soil moisture. And what this plot on the right shows is that when we do the soil moisture data assimilation, we get an improvement in the agreement between the root zone soil moisture and NDVI compared to when we just do an open loop or unconstrained model run. So that's just a neat way how we used NDVI as an independent verification that the model is doing something right in the root zone. And just on that example, that was research we did about 5-6 years ago. It made its way into the Bureau of Meteorology and is currently the only operational system in the Bureau of Meteorology to produce soil water products. Here is the Australian Water Outlook at the Bureau of Meteorology. It gives us water balance components, particularly, note, the root zone, gives us a reanalysis up till the start of the 20th century. But more importantly, the data assimilation component, soil moisture data assimilation, where we assimilate ASCAT and SMAP, soil moisture retrievals, it give us the 9-day forecast water balance out to 3 months water balance estimates. So that's currently the only. I should also add that there is a static tree and grass layer that was derived from the MODIS product, but that hasn't changed for, well, a long time. Another example that we're heading into, the Bureau of Meteorology have been custodians of a network of daily rain gauges. We generate gridded analyses from these rain gauges and put them on our website daily. And on the top left here, I hope you can see my mouse, is a rain gauge analysis. It's an interpolation of between all the gauges, and there's probably about 4,000 gauges recording daily rainfall for Australia any given day. And so what we thought is, now that we're moving into the requirements, so that we need sub-daily information, and we need to drive our land surface models, that we might use the product from the iMerge, GPM iMerge system to disaggregate the daily rainfall into, well, hourly rain rates. And so what we're able to do for the 25 years or so of iMerge data, now that is comprised of the TRIM era and the GPM era precipitation products. We bring them into our systems and we disaggregate the daily data such that it adds up to what we get when we get the interpolated surface. So it's just a way of demonstrating that we can use the satellite data, disaggregate a daily rain gauge analysis to give us how the rain fell over a 24-hour period. Now moving to the work of my colleagues in New Zealand. If they are online, please jump in. This is new stuff to me because it might surprise a lot of you. There's not much demand except for a very niche area in Australia for snow water products. But what they've given me to show here is a sort of, if you like, a radar-derived before and after, or the snow-free and snow-covered imagery, where you're able to then infer the snow depth, which can then drive their moisture, well, their water balance modelling from that. I hope if I've probably grossly misrepresented that, but please take it up with my New Zealand colleagues for more information. This one I'm a little bit more familiar with. So this is using SAR imagery, vertical, horizontal, and polarized data before and after a flood event. You can see that before you see a rise in the hydrograph on the top left, and imagery taken before on the bottom left. In the middle is almost at the peak of flood extent, right through to the recession. Several images, and you can look at the quantities of data of water that have moved through the landscape there. And finally, they are also soil moisture hungry people. They use the satellite-derived products, the reanalyses from various agencies. In this case, it's the ERA 5 soil moisture, but they've also got an in situ network of soil moisture observations too, that they all munch together and do their analysis. We at the Bureau of Meteorology are moving more and more towards a land surface model-based approach to our water resources assessments. And that is pushing us further towards this idea of being able to better integrate with the atmosphere and ultimately NWP. So we want to know how good the JULES is the UK Met Office developed land surface model that's part of our Earth system model in Australia called Access. But I'm arguing that by moving towards a land surface modelling approach for hydrology, it affords us more opportunities to use Earth observations from all parts of the electromagnetic spectrum, from the optical, vegetation-related information, surface property information, through to the microwave of soil moisture and precipitation. And so we've already seen in the previous presenters the range of Earth observations that are available, from the radiances through to the derived products. I just want to highlight that I believe a underutilized resource for Earth system science is land surface temperature from geostationary satellites. I think we should do a lot more of using those data to constrain energy balance, at least on a daily data. And yeah, brightness, temperature. So we've seen all that sort of stuff before. We are testing this hypothesis that through better estimates of land surface cover, particularly the fractions of plant functional type, we get a better modeling capability of the land surface. It might seem an obvious statement, but when we look at what Joules is currently run with, what it was run with, what it currently run with, and what we're proposing it ought to be run with in Australia, there are significant differences in the representation of some of these plant functional types. And so my colleague Siran has led the charge of implementing some of these improved plant functional types in the Joules model. And what these plots show for a location in Northern Australia, that by using they call it the Joules BOM PFTs, plant functional types, we get closer agreement with the top, it's latent heat flux, and at the bottom, sensible heat flux. We get better agreement with our in-house derived PFTs than if we use the IGBP derived or the CCI derived fractions. And the similar story with soil moisture. The blue curve moves a lot closer to the observations, particularly for the root zone moisture on the bottom right. So wrapping up, we've got a range of approaches to utilizing hydrological or earth observations for hydrology prediction, from evaluation, where we can use ad hoc observations and the like, through to calibrating models or identifying parameters that are important, and then right through to the forcing and the assimilation. Currently, the use of Earth observation seems ad hoc. There's, say, SAR, for example, is used for flood inundation mapping, and that's that's independent from, say, the soil moisture or the evapotranspiration, for example. The Earth observation will be used in these ad hoc applications. The land surface modeling is a way of integrating those multiple data sets. And we're proposing that it ought to be the way we do hydrology, at least in the Bureau of Meteorology. So we've taken the initial steps towards changing the land cover representation, primarily through vegetation-derived Earth observations. Oh, I hope it makes sense. It's very late at night, sorry. I would think as well that the diurnal variations, seasonal and spatial variations of the landscape are a good way to constrain energy balance. So more utilization of the land surface temperature as a core satellite observation. And of course, the soil moisture. We saw in the previous presenter's slide that there was core observation was identified as the root zone soil moisture. There is no such thing as Earth observed soil moisture. It is through the constraint of the surface layers through the observations that we can propagate the improvement to the deeper soil layers and give us root zone soil moisture estimation. I'll stop there. Thank you very much.
Thank you, Luigi. Excellent presentation, very informative, and thanks for your table giving the overlook of the observations you used from the satellites. Any questions to Luigi?
Everyone's taking pity on me because it's so late at night.
Okay, there is one. Go ahead, Marcelo.
Sorry, me again. Thank you very much, Luigi. Excellent presentation, and I enjoyed it a lot. With reference to one of the first slides with the big arrow you showed, in the right part of it, the focus is on the use of satellite data for forcing and also for assimilation into predictive models in hydrology. there's always the issue of the latency of the satellite data or products.
Yeah.
Compared to the temporal response or time response of the basin. Is that an issue you face, or how you deal with that?
That's a great question. The issue is with when we try to use Earth observations for forcing. Soil moisture, because of the nature of soil moisture, it's got a longer memory. So the latency in soil moisture products isn't so much of an issue. The disaggregation of so the real-time gauge analysis with satellite observations, well, it is a challenge. The iMerge data, particularly if we use the higher quality products, has latencies of 12 hours or more. Now, maybe for some hydrological applications, that's not too bad. But what we're proposing is we move towards geostationary derived rain rates, whilst they may not be as accurate in some places as the microwave derived precipitation. We're going to argue and evaluate whether it still can do the disaggregation of that daily real-time data. It's to be explored, but yeah, moving towards more real-time applications, satellite observations will increase the uptake of the products we develop.
Great, thank you.
Thank you. I had also a question. Together with the GPM data which you are using, are you using together with that your ground-based radars, because you have many radars, and especially on the coastline, you get the advantage from there for the soil moisture and precipitation.
Yeah. Anyone familiar with Australia, we have very rich information rainfall around the edges. There's big holes in observation network in the center of Australia. So what we're in another project, my colleagues are looking at combining the radar network, which is that has a gap in the middle, so we're getting radar derived rain rates and satellite derived precipitation, probably from Himawari. Geostationary. For Australia, it's Himawari. Yeah, and merging those data in some way. It's still a work in progress, but some preliminary work my colleagues have done with University of Melbourne is demonstrating it's achievable and yielding some good results. So yeah, we're looking at filling in the gap between the observing network with satellite observations.
Thank you. All right, I think it's time to move on. So the next presentation, we have satellite-based hydrological applications from Asia, presented by Fu Wang from CMA. So floor is yours, Fu.
Thank you, Mr. Haki. And can you see my screen right now?
Yes, we can see that, but not in the presentation mode. So it's in the normal.
Oh yeah. I will show it. It's a great pleasure that I will thank the organizer for this opportunity in giving us the opportunity to exchange ideas. I've been giving the name the core hydrological observation applications from the perspective of NWP. So this title is somehow a little bit broader than the topics of this session, and I will I hope that my presentation is well aligned with this thing. If some aspects appear slightly broader or outside of this topic, I sincerely appreciate your understanding. And I also have learned about the former presenter from Bonn, Lucy. I think their presentation is very enlightening, And I might giving my presentation in three components. First is the satellite observation presentation plans of CMA, and then I will give in a brief introduction to NWP systems we've been doing in CMC, and also application case of hydrological data and assimilation into an NWP system. So first part, the current sorry, that seems that something is missing. Currently, we have Fengyun satellite constellation like 10 satellite, 5 GEO and 5 LEO satellite operating in orbit, and they are aiming at for water vapor and cloud and precipitation observations for short-term nowcasting, and also we got LMI observations aiming for lightning and severe storm observation. And also we have a special LEO satellite called FY3G. That was the first first satellite with a capacity for precipitation measurements in China, and it could demonstrate a 3D structure of the precipitation system. And here is a demonstration of a case that in May 7th, 2023. And the structure of the precipitation is well captured by this spaceborne radar. And also we have been NSMC, the National Satellite Meteorological Center, have been organized such an agile remote sensing application platform that providing some supporting mechanism for providing Fengyun meteorological satellite for desert prevention or something, etc. It's concerning about sandstorm and water color, typhoon, and the snow and a cold wave, etc. And that is how all these remote sensing applications will be easily accessed and could be shared with someone who is in need. Secondly, I will talking about the foundation of our center. It was initiated in 2021, and we have been working together since 2022. And the researchers are from 10 institutions from CMA and its branches. And we were working to building up to build up CMA's national NWP system, and mainly there are two: that global forecasting system for a 85 layers and top to 0.8 par, and there another one is a regional mesoscale called CMA meso with 1 kilometer resolution, and it's running 8 times a day, and with 1 hour data assimilation durations. And now we have been assimilating observations all over the world, and thanks to WMO's coordinating efforts, we can assimilating regular observation all over the world, and from GEO's observation with AMV and the radiance. Also, the ocean wind from Fengyun satellites, also colleagues from our Euron satellites. Also, LEO observations of microwave soundings, hyperspectral soundings. Also, the GNSS observations. The efforts of the satellite data assimilation builds the forecast capacities, since the more satellite data has been used in the DA system of CMA GFS. Its difference against the EC and the NSEP is now narrowing down. So that means more satellite data might help us to understand of building up our forecast capacity. And this is also the building up the capacity for precipitation forecast. And also we now have a RTM radiance transform model called ARMS to support satellite data assimilating. And now it's also coupled with CMA GFS and the CMA MESO. Both the global and the regional NWP systems is now all operational. And in somehow that since it has been we have been closely working with NSMC, so we have find that Fengyun satellite instruments have certain specific settles about its spectrum response functions. So it's somehow corrected the misunderstanding of RT-TOFs, and its radiance simulation accuracy surpasses RT-TOFs in somehow. And the second part, the third part is about the sound application cases. First of all, because of satellite assimilations, we have been able to narrow down our errors of typhoon forecast, and it has lead to a steady year-by-year improvement in typhoon forecast accuracies. The second application cases I've been giving is now we were doing precipitation assimilation in NWP systems. And first of all, we have been using AI technologies to build up an observation operator using the NWP variations like relative humidities, temperature, and wind fields to build up precipitation simulation capacities. We can find that the operator performs well in simulating light, moderate, and heavy run rates. That is giving the NWP's capacity to somehow fulfill the capacity of precipitation forecasting, like the last presenters have been talking about the Australians. In some places, we are lack of observation, and we try to get some data from that place. Somehow, NWP system with such kind of observation operators can help us to get that information. And now the following part, we were using this the observation operators to simulate precipitation to our CMA regional models, and we can find that in the place where our we have some precipitation observation, not only the longitudinal profilings, also, as well as the latitudinal observations, we can find that the humidity has been increasing when we are simulating this precipitation data. But it's only primarily affects to the middle and the lower troposphere compared to the control part, that means control experiment, which has been which in FY3 precipitation is not assimilated. And when we were doing month data assimilation and forecast experiments, we have found that though there are not enough satellite data yet that being assimilated to this model, the FRAG score, TS code for light, moderate, and heavy rainfall are comparable to control experiment, although and it's a rainstorm for larger rainstorm, severe rainstorm events, it's improved very pronouncedly for maximum increasement up to 99.9%. And also we have been giving another case here. That was the observation results, and this is the upper left was the observation, and the lower left one is the control of our forecast system. And we've been giving three experiments. The first of all, the upper right ones was assimilating Fengyun 3G precipitation at 9 sharp, and the lower middle one was simulated emerge precipitation at 9, and the lower right one was assimilating image precipitation at 0, 3, 6, and 9 hour. That means that the TS score shows that emerge 9 and FY3, these two experiments shows that if we have been assimilating observations of precipitation with a wilder range, with a better coverage, that will improves the precipitation forecast capacity. But when we are putting more frequent precipitation observation, it seems that the opposite way. That means that the forecast capacity has been reduced. So it raises another question that maybe choose observation with caution, or choose the observation with certain frequency is even more important. And in the future, because we were doing a Earth system modeling and the prediction in the future, and we were requiring more and more observation data, not only for the atmosphere, but for the from the land, the biosphere, the cryosphere. And I think the key is more core observations or more reliable observations, and it should be at the right place. Thank you. That's all for my presentation.
Thank you very much, Fu-Wang. Great presentation, very informative. Do we have any question to Fu?
Excellent presentation.
All right.
I would just
Go ahead, Liang.
Yeah, excellent presentation. I would just suggest that for question and answer, maybe put on the chat, because we are a little bit behind schedule. Thank you.
Yeah, that's good. Let's continue. Thank you, Fu, again. The next presentation is about assimilation of satellite data into hydrological model by Juye Kumar from NASA. So, Juye, are you online?
Yes, I'm here. Happy
Okay.
to share the slides from
Very
my
safe.
screen. All right, hope you are able to see that.
Yep,
So
it's good.
thank you again for inviting me to discuss this. I see a hand up from Li Hang.
No, go ahead, please.
All right. So I'm a scientist in the Hydrological Sciences Lab at NASA's Goddard Space Flight Center. So I'll talk about some of our work in assimilating satellite data into land and hydrology models. So the previous speakers made a really good case for why this is important. I'll offer a slightly different perspective, kind of going back to the hydrological cycle that we all grew up with. And so this used to be the picture of the hydrological cycle that represents all the different processes at play. So the U.S. Geological Survey retired this figure a couple of years ago, and they introduced this new figure that really captures or acknowledges the human impact on the water cycle. So the main difference, if you compare the two, are the ubiquitous nature of human processes, things like agriculture, groundwater pumping, urban runoff, and so on, and in the industrial water use. So it's sort of, we all know this, that this is a big factor in the water cycle. So this modification to this figure kind of adds that explicit acknowledgement. So if you think about these sort of processes that are at play, whether it's industrial water use or groundwater pumping or agriculture, they're all human-driven and they're all subjective. So it's really hard to parameterize them in models and really, capture, because we don't know when the farmers are going to irrigate. We don't know when people are going to do the pumping. So that's where observations become crucial. And I think so in addition to improving the processes in the land surface and hydrology models, I think of these observations as key to really capturing the human management and the impact that these processes have on the water cycle. So, and we have, again, evidence of how prevalent this modification is. So this is a map found from NASA's CDAC website, where it shows the extent of human modification on the Earth's surface. So you can see that almost 95% of the land surface has been modified in some form or the other. And obviously, this has a huge impact on how the water and energy fluxes on the land surface evolves. So that's been our focus, to think of these assimilation and the use of these observation as not just for improving the processes, but also for capturing some of these management impacts. So this is an example from one of our earlier work where we assimilated remote sensing data sets of vegetation, leaf area index and vegetation optical depth, which you get from optical sensors and microwave sensors. So what you're looking at is the impact of the assimilation on evapotranspiration. So when you assimilate vegetation data sets, what sort of impact it has on ET. And these figures are designed so that warm colors indicate improvements in ET as a result of assimilation. So the darker red colors indicate that you have much larger improvements in ET. And the interesting thing is that there is a spatial, the spatial patterns of improvement that you see are highly correlated with the agricultural areas of the US. So on the left side, you had that figure where it shows the major agricultural areas of the US. This sort of blue area is called the Corn Belt. That's where a lot of corn agriculture happens, and the soybean and so on. So really what this figure shows is that when we assimilate vegetation data sets, it's capturing the shifts in phenology and seasonality that's introduced because of managed agriculture. And that's, again, hard to capture this with models alone, because natural variability driven vegetation changes often do not accurately capture what's happening because of human induced changes. So this was interesting because, again, so this result showed us that simulating vegetation data sets or other data sets can actually indirectly help us to capture these impacts. So we have been focused more recently on assimilating more data sets and moving towards sort of a reanalysis for the land and hydrology. I know we have a lot of reanalysis products out there, like MERA2 and ERA5, which are mostly focused or only focused on atmospheric assimilation. In both these products, there is no land surface assimilation at all. So we have been working on, again, sort of reanalysis efforts focused on land hydrology, taking, in this case, taking the MERA2 and GPM data as the boundary conditions, and then assimilating a lot of land remote sensing products simultaneously. So in this version that we developed, we assimilated soil moisture data from multiple sources, vegetation data sets from MODIS and Terra and Aqua, and estimates of terrestrial water storage changes from GRACE and GRACE follow-on missions. So we assimilated this into a NOAA land surface model. NOAA land surface model. And this is a sort of high-level results that came out of this reanalysis, where we try to capture the non-stationarity, which is defined as the changes or shifts in your distribution. So, for example, so if you are looking at, let's say, water storage in this case, how is that PDF, probability distribution function, shifting as over in this last couple of decades? So what I'm showing here is called a non-stationarity index that kind of depicts the degree of shifts in the water cycle that is observed from this reanalysis in the last 2 decades. So the non-stationarity index of 1 means there is a high degree of shifts present, and 0 means you are fairly in a stationary condition. So this analysis, you can see that when you look at this map, you can see that the non-stationarity effects are very regional. There are strong regional patterns to these, places where we see this high degree of non-stationarity. And there's a paper that is published in PNAS, and you can read the details there and the details of the math. But one of the other main findings that in this paper was that when we tried to find attributions to these non-stationarity changes, most of them were actually related to management impacts. So again, kind of to explain that further, so on the left is that non-stationarity map that we observe for terrestrial water storage. And we applied the same thing to precipitation, which is one of our key driving meteorology input, right? So, and if you look at the patterns in non-stationarity and precipitation, they don't necessarily line up with what we observe for water storage. And so the point is that the non-stationarities that we observed in the water storage is not all coming from the driving meteorology. So there is, beyond the climate variability as a factor, there are management impacts that actually really influence what's happening to the land surface. And we see the same thing on ET and runoff. Again, the type of the degree of non-stationarities and the locations where they occur are vastly different for different variables like ET and runoff. So, and this is an example of why that is. So let's say we look at this map at the top that shows the major agricultural areas and in irrigation where irrigated agriculture is dominant. So in northern India and eastern China, these are some of the hot spots. So if you look at the changes in water storage, which is on the left here, you can see a big depletion that has been happening in the last 2 decades. And at the same time, when you look at the vegetation changes, this is also informed by remote sensing, you see an increase. So what's really happening is you are pumping out water to sustain the agriculture in that region. So therefore, the water storage is going down, but on the other hand, vegetation production is going up. So if you think of what this means for a variable like evapotranspiration, on one hand, you have less water available to transpire. So you expect, if it is solely driven by groundwater pumping, you expect the ET to also go down. But that's not what's happening, right? So we pump that water out and mitigate the surface stress, and vegetation is picking up. So therefore, you expect ET to go up. So for a variable like ET, you have these sort of conflicting impacts driving the changes. And then when you look at the reanalysis, we end up having a muted signal on ET, sort of slightly going up. So what I'm trying to say is this is why assimilating multiple constraints on the water cycle becomes important. If you only assimilate GRACE data, it's going to show that your water storage is going down and ET is also going to go down. If you only assimilate vegetation, you're going to see that vegetation is going up, ET is going to go up. But to really capture these conflicting impacts and mostly driven by management, we have to have multiple constraints on the water cycle. So now moving to some more interesting or more recent work, we have been focused on assimilating data from this new mission that NASA launched a couple of years ago called Surface Water and Ocean Topography, which is a partnership between NASA, Canadian Space Agency, and CNES and the UK Space Agency. It's a new concept. It's a wide swath interferometric altimetry. So it's really going to give you all weather measurements of the water bodies. And I'm going to focus on the hydrology part of this. So the direct measurements from SWOT includes water level, slope, and width. And indirect measurements include the water discharge that, or the river discharge, which is what a lot of hydrologists want. So just to give you a perspective of what this is really transformative for hydrology. So you can see on the right a map over France that shows the number of measurements, number of observations in the rivers during a 21-day cycle. So you have multiple repeats that you get in many places. This figure on the left shows the comparison of the coverage from SWOT compared to the classical altimetry measurements that we've had. Which is very thin. You barely get that thin swath, but compared to the measurements from SWOT, you're going to get a much better coverage over the water bodies. So this is a sort of pretty picture of what this is going to mean. Some early results. We've only had a year plus of data from SWOT. It gives you a coverage of the mean flow of global rivers as seen by SWOT. I think it is transformative because, one, you have observations on all these river bodies, and we all know that measurements across transboundary basins is a huge problem, right? Countries don't share the data, and for the first time, we are going to have measurements across all these transboundary basins. And third is that these measurements are also going to be indicative of all the sort of human modifications on the river bodies. Almost all the rivers are dammed. There are reservoir operations. We don't have reliable data to constrain those estimates. And this is where I think SWOT's going to be pretty awesome. So another early result from assimilating SWOT data. This work was done just over the Ohio River Basin in the U.S. And these charts show the improvements that we obtain as a result of assimilation. So the blue line, so if you focus on one of these metrics, let's say the percentage bias, the blue line is the open loop, the model without any assimilation. And then you have a couple of different assimilation runs. The black one shows data assimilation of SWOT with some localization, which means we figured out a way to propagate the assimilation improvements upstream into the river channels. And then on the right, and the third one is the SWOT discharge product. So the SWOT mission also produces a discharge without assimilating through empirical algorithm. So the exciting result here is that we see a much better improvement from assimilating SWOT datasets. The black line generally looks the best in all these comparisons of different metrics. So the point is that assimilating the water level data, which is the mission product, not just improves the water level estimation, but also improves the river discharge that the model is able to produce. Another work that we are focusing on is to look at developing snow constraints. So I know we've had a lot of measurements of optical data, snow cover measurements from MODIS, but we don't really have a good high quality measurements for snow water equivalent, which is really the snow mass constraint that we really need. So using machine learning, we developed an estimate of SWE data at a 1 kilometer resolution by using some reconstruction approaches. So this is an example. There's a paper that describes this work. So this is a 1 kilometer product that we have developed. On this CDF shows the skill of the product, which is now we call it LSTM because it's based on a LSTM method. It generally looks very good compared to some good reference data products out there. You can also see a pretty picture comparison here where we compare the LSTM-based product to some model products like ERA5 and HydroGlobe, which is a NASA-based product. And you can really see the spatial features that are captured in this LSTM product. So we are using this as a constraint in our multivariate reanalysis. So building on that earlier product that I described, we are now focused on the next version of this reanalysis that's going to include more remote sensing products, of particularly this snow product that I talked about, and simulation of SWOT, water extent, and sort of building on all the other remote sensing simulation we already had. And so this is currently being produced at a 5-kilometer resolution. We expect this to be finalized by summer sometime this year. So I'll end with this. So I'm particularly beyond process improvements, I want to emphasize that I think land of data simulation is crucial if we are to capture the impact of management, because that's where observations probably has a unique value. And I also argue that multivariate remote sensing and data simulation is important because in many cases, the impact on the land surface is complicated and multiple constraints are necessary to really get at the right attributions and capturing the complex impacts that management and the natural variability that has on the land surface. So I'll stop here and happy to take any questions if there's time.
Thank you, Surya. Very impressive to see these SWOT results and the new data in use. Yeah, we are a little bit late, but if there are any quick questions, let's take one. Go ahead, Sean.
I'll have this as 2 questions. One, do you see a follow-on mission that NASA might, I realize you're just starting to get a lot of your SWOT data, but particularly for operational centers, it's good to be able to understand if this is a continuing mission that we can hope to rely on into the future. And 2, I was particularly intrigued by the machine learning approach to snow water equivalent. Just wanted to see if that, it seemed like everything was trained on MODIS. I'm wondering how applicable would the same algorithm, and I haven't read the paper yet, so you just pointed it out to me, but how applicable would that be to VIIRS or some of the satellites that with MODIS getting a little long in the tooth, so to speak? I think it would be good to be able to know that there could be the same approach developed for another satellite that is operational. Thank you.
Yeah, thanks, Sean. So SWOT question, yes, it's a fairly new mission. So it's a bit above my pay grade to answer whether, what NASA's plans would be to for a continuity mission. But I think, this is a big discussion in the community, right? The continuity versus new missions. But I think, one of the point here is that SWOT data gives you the water surface elevation within a few hours of retrieval. And whereas the discharge products that the community produces has several months of latency. So that's not really viable for operation. But so if you are able to assimilate a water surface elevation, it gives you a quick path to impacts on operational systems. And your second question on the MODIS V, so this data was trained with snow cover to an operational, no, I'm sorry, not an operational, a sort of Landsat-based reconstruction. And yes, I mean, we are actually thinking about extending this to VIIRS now that MODIS is on its last legs. So we do want to have, plan to continue to produce this based on VIIRS.
I think we need to move on. Thanks for your presentation again. Next presentation is about the use case in Africa for hydrological applications, satellite-based hydrological application, and it's presented by George Gulemuga. The floor is yours. Thank you.
Thank you.
You want to share or should we share slides?
Yes, I think
Georgia,
yeah, have my
should I share?
presentation. We can
Okay, yeah, that's
go
great.
directly.
Yeah, yeah, I can. Can you see my screen?
Yes,
Yes, it's
at
good.
my side, I see
Yes.
clearly. Thank you. I have some issue with the connection. We are in Africa. We still fighting with the issue of internet connection. So I think since the beginning of our workshop, of the presentation, it was the matters relying on modeling and so on, more research and the results. But now I will give an insight on the practical use of the satellite data. The next. Yes, it seems to be a long content, but we will pass it very quickly. And to catch more what we did, I just first of all to thank the organizer who associate us on this exercise to present what we are doing with satellite data in Africa. We are so exciting on it. And we just like to give a brief overview of the Congo Basin. And also I will say thank you to Kumar, who introduced me with the issue of sharing data in most of the transboundary basin, as we are facing the same issue in the Congo Basin. As we can see, is one of the large river basin in the world, the second after Amazon, with 10 riparian countries. And the average discharge is estimated by 41 cubic meter per second. Yes, the second. So now the Congo Basin is known as the first hair flock, because the last 2 years or 3 years ago, with the last COP, after many research, the result was that the Congo Basin is kept more dioxin of the carbon, but in the Amazon is delivering more than to keep it. So the Congo Basin is considered now the first lag of the earth. And what is important, what we focus on the use of satellite data is this potential of navigable channel in the Congo Basin. And this, as shown by Kumar in the map of SWOT satellites, we have large and big rivers in Congo Basin, and to play a key role for the blue economy through the transportation. So most of the country are closed and opened only by inland waterway. We can find also the hydropower estimate at 150,000 megawatts. So we can find also the millions of hectares of humid part in this basin, which are in the good position regarding the world. Yes, it's for the first, the second, yes. So since 1999, there's 4 states, head state of 4 riparian countries: Congo, DR Congo, Congo Republic, Central African Republic, and Cameroon.
decided to create a CICOS, the International Commission of Congo Basin, with two mandates to promote the inland navigation, but also the integrated water resource management. So now the International Commission for Congo as a river basin organization has 6 country members and 1 observer who is Zambia. So we have Angola, we have Central African Republic, the Cameroon, we have Congo and DR Congo, Gabon, and Zambia as the observer. Yes. So International Commission of Congo Basin has a mandate to coordinate regarding the hydrological monitoring in the Congo Basin, is to facilitate the access to health data, to support the national hydrologic services, and to centralize data and disseminate it through the hydrological information system. And also, as we will see in the map, to raise the awareness among the country on the data monitoring, also data sharing, and to promote the innovative technology for data acquisition, like spatial altimetry, and to support the capacity building of the stakeholders in the Congo Basin. Yes. As you can see, the status of hydrometric network in the Congo Basin, we can see that just by 30 in situ station, by 1960, the basin has more than 400 in situ station, hydrometric station. But because of many issues, the political, social issue, the hydrometric network collapsed. So we can go to the next. So next. The next is I have some problem of connection. Yes, as I said, as I said, the first one, we pass up. Before this one. So yes, as I said, yes. So for this satellite data is your opportunity for the transboundary basin, because you need to monitor the hydrological parameters through in situ data costs very, very high. So with the AU Earth observation, we pass through the 30 station to more than 1,000 station. This is the virtual one, as demonstrated by Kumar, with the many missions like SWOT, as he said. The next. The next. Yes, as I said, that the river transportation play a great role, the economic role in the basin. So that is some the data we have in the sector. We consider that the river transportation in this humid zone is very, very cheap than others. And most of the part of population use only the river transportation for the travel and economic exchange. The next. So the sectors, the river transport, we face more problem as the river basin organization with the mandate to promote. So after the many analysis, we saw that there is an enable nautical information service in the sector. Reliable also nautical chart to get the owner of vessels, and several navigation incident and accident, lower water level due to the climate change, and poor channel marking. So that is the most problem we identified at the time, and we decided to build some information to support the sector. Next. So we start by 2015 to set up a water system, hydrological system in the basin, is now called the JERNAC, Water and Natural Resource Management in Central African, that offers some geospatial services. So we made a lot as maintenance of virtual station, provided the water level to the Congo River. We selected just the main tributaries, Ubangi, Sanga, Kasai, and Congo River itself. And we use also the measured data, in situ data, and reporting some symbol on the map. We elaborate and collect the observation or the feedback from the boaters. So that is the some job we did to support the sector. The next, and we can see some mission, the satellite data mission, Sentinel 3B, Sentinel 3A, because our focus was on the water level, what is very, very important for vessels to navigate. So the methodology we use to collect the data, and mainly water level, as I said, from spatial altimetry, and we did some analysis of the time series of that data. Mainly in the past mission, we use from Sentinel-1, Sentinel-2, and as we can see, because most of the mission in many parts are not really validated. As Kumar said, for SWOT, Sikos was selected as the transpondary basin who was in charge of to validate the SWOT data, water level data from SWOT, because we set up two in-situ stations to validate that data. So we use 88 primary virtual stations to define the intersection between the river, and the reporting of the navigable symbol, also collecting the data, as I said before. The next. So the navigation aid system using satellite data has the objective to strengthen the capacity of international commission member states to use health observation data for river navigation safety, and as many deliverable was the JERNAC web portal and the JERNAC application, the smartphone application, to help more users to use it and to navigate safely. Next. So this is the list of some data from all these missions. As I said, the radar one, we make the optical, but the focus, as we said, is on the ultimately data. And we elaborated three main services, but today I'm focused on the monitoring of water level for navigation river. But we elaborate some services on the monitoring of hydrologic balance and of our region, but also the monitoring of the dynamic of a flooded area under forests of a Congo Basin. Next. That is the line of methodology we use. We mix the institute data and the AO data and the process through some analysis and using some modeling, the regression modeling, and we develop the product and disseminate it to the end users and decision makers. Next. That is the same line. So we have the entries using data from Sentinel-3 and 6, Sentinel-1, the radar 1, and the intermediate. We get the intermediate product, and there was some treatment and exact. That is the line of the methodology and some data and parameters used to reach our result. I will show in a few minutes. Next. So as I said, our services, the navigation aid or assistance to the river transportation, we use 4 main tributaries, Ubangi, Sanga, and with the data from these machines. So that is the many results we get. We can go through. So yeah. Yes. So we found it was the good overlap between the 3 virtual stations we selected in the part, but also the good correlation with water level recorded at some part like Kisangani and the kilometer point. We call it the PICA for navigation. So we compare the data because the source of data, the platform who provide freely the data is Hydroweb. As said by Kumar, the data of sorts, we can find it freely on Hydroweb platform. So we compare all this data to find the good correlation for the prediction from the section to another section. Next. Yeah, that is the same correlation analysis we did between some time series on different sections of the river. Some simple model we use to improve the result. The next. Yes, that you can see here the internal module and the innovation, the tensor and the measurement between the maximum water level, the height, max and the minimum. So, but also the slot between different sections. The next. So our mission was to get the usable services which can be used by most of the end users who are the owner of vessels who are navigate on this rivers we select. So we got the freeware navigation smartphone, so which is used by more than 2,050 end users today. The next. So we found the many benefits and advantages generated by this navigation aid system information. So the feedback from the users was that the reduction and elimination of some losses, and there was the optimization of vessel traffic, the increasing of the trade exchange between different cities in the basin, but also it promotes the integration of the economy of this entire region. And we found also a drop of the price regarding the agriculture one, because between the village to the cities, without vessels, the price of agricultural products were increasing. But because now there is more vessels who are traveling easily on the river, we find the drop of agriculture product price, and also the reduction and the elimination of many accidents registered in the past. So we also use our best to train the captain of the vessels how to use this system. The next. This is the global, our platform, JERNAC platform, apart the navigation aid system. As I said, we elaborate other geoservices regarding the monitoring of water balance and the flood, fire, and so on. So this is our platform where we can find many other services to elaborate using the satellite data. The next. Yeah, that is the cluster of that geoservices we can find in this system, apart the smartphone for the navigation using the water level. Next. I think it's the end one. Thank you for your attention. This is the circle of the list of our founder, but the technical partner we are working. Thank you very much.
Thank you, George. Very informative presentation. I think we are now very much behind the schedule, so we move on. If you have any questions to George, please drop them in the chat. So we need to unfortunately move directly to the next presentation, which is by Simone Gabellani about the satellite-based hydrological applications from Europe. So floor is yours, Simone.
Yes, thank you. Good afternoon, everybody. I will share my screen. Do you see it?
Yep, it's good.
Yes. Okay, perfect. I'm Simone Gabellani. I'm a researcher at CIMA Foundation, and I'm here in place of Silvia Puca, that of the Italian Civil Protection, that is the manager of the HSAF program. HSAF is one of the 8 satellite application facility of EUMETSAT. The other are devoted to land surface, climate, atmospheric, ocean and sea highs. And the HSAF is devoted to hydrology. And it is a consortium. Several institutions participate to the development and the distribution of the satellite product for hydrology. The outline of the presentation, I will show you today the HSAF portfolio, the product that we develop, distribute, and validate. And some application of those products for hydrological purposes. The SAF, the HSAF generates satellite data for 3 hydrological parameters that are the precipitation, the soil moisture, and the snow. There are 2 big families of products. The first family is the near real-time products, distributed with different temporal resolution that are product with the temporal resolution of the day that are distributed in real time, but also precipitation product with a temporal resolution of 15 minutes. And then the second big families of data is the data record. Especially we have data record for soil moistures that are consistent data set that extend back in the past from 1992 or 2007, that are usually used for climate analysis. One of the characteristics of the HSAF is that we perform a quality assessment and the validation of the products every 2 years. The team, the activity are organized in 2 teams. There are teams that we call cluster that are a group of institutions that are dedicated to the production of the satellite data. So we have a cluster for precipitation, a cluster for the development and the distribution of soil moisture, and a cluster for snow. And then we also have a cluster of partners that are dedicated to the quality assessment and the validation of the products. I will briefly introduce some of the product that the HSAF develop and distribute, but we have a lot of other products, more than 100. About the precipitation, most recent product are those 2. EUMETSAT HSAF PINFCI. We identify the product with the code H40 in this case. So this product is the instantaneous precipitation maps generated combining geostationary infrared data and microwave on LEO satellite. This provide the precipitation, instantaneous precipitation with a time resolution of 10 minutes, and is based on Meteosat 3rd generation. The H42 product is the cumulated values of the H40. In this video, you can show that the previous operational product that we have based on Meteosat 2nd generation on the left of the screen. On the right of the screen, you see the instantaneous precipitation based on Meteosat 3rd generation. You see quite well the improvement in spatial resolution. So this is a precipitation event in Africa. And then we have another set of another satellite precipitation product based on HASCAT. So it's indirect measurement. It's based on a top-down approach in which the variable is the best scatter of SCAT, and then an estimation of the daily precipitation is produced. So the H64 product, it's a product of cumulated precipitation with a spatial resolution of 0.25 degrees, and it's the daily amount of precipitation. For which concern the soil moisture, we have two main families. As you know, the satellite is able to estimate the soil moisture for the first strata of soil, so for the first few centimeters of soil. And we have several products for the surface soil moisture. We have both near real-time product with different spatial sampling. The spatial sampling range from 25 kilometers to 6 kilometers. And then we also have data records that are consistent, a consistent data set of surface soil moisture from 2007. The surface soil moisture is purely based on ASCAT retrieval, so it's purely satellite data. While the second families of soil moisture product that HSAF produce is the root and soil moisture. Is produced by CNWF through the assimilation of the surface soil moisture into the land surface model that they daily run. So in this case, the soil moisture is expressed as a liquid soil wetness index at four different depths, from 0 to 7, from 7 to 28, from 28 to 100, and below 100 centimeters in the soil. The products, it's we have a near real-time product for the roots and soil moisture with the 10-kilometer resolution, distributed daily. And then we have a data record from 1992 up to now, with the same resolution. Yeah. And about the third family of product that HSAF developed is connected to snow. Mainly the snow products are devoted to the estimation of the snow cover. I know that later on this afternoon, Mattias Takala from FMI will have a presentation, and he will show with greater detail the product that are also developed in HSAF. So I will not spend too many words on that, but essentially we have effective snow cover by risk infrared radiometry, and that cover the North Hemisphere. And we also have a product that estimates the snow water equivalence for Europe. As I mentioned, the HSAF not only developed new product and distribute those products, but also activity connected to the validation of the data. And every 2 years, the consortium validate all operational products, and we have different technique for evaluating the goodness of the product. For example, the precipitation product are compared to ground data from rain gauges and to data from meteorological radar, we have the whole European network of ground radar observation, but also the data are compared with other satellite missions. About the soil moisture, every 2 years, the operational product are compared to ground data through the Soil Moisture International Network, but also we validate the product using a triple collocation analysis. So we compare each operational product with soil moisture data from passive measurement from the Climate Change Initiative, and also with the analysis of from land surface modeling from GLDAS of NOAA. And about the snow, the validation is performed by comparing the snow cover area estimated by the HSAF product with other satellite data like Sentinel that has a lower, a smaller spatial resolution, but are affected more by the cloud problems. So we usually consider the Sentinel data as the benchmark. We validate for the data in which the cloud cover is negligible, the HSAF products. This is just the next slide. I will show you just some examples of the product. This is the H60 instantaneous precipitation. So the product that uses Meteosat second generation, not the new one, available on the EUMETSAT EUMETView, together with the Lightning, available again on EUMETView, so the platform for the visualization of the products of EUMETSAT. The Lightning is not generated by the HSAT consortium, but it's important. Those data can be used for monitoring the evolution of events, especially in regions where we do not have a consistent ground measurement network. Among the partner and in Europe, those data, the satellite data, especially precipitation, are used for the monitoring of the events. Those are some examples for the Mediterranean cycle of 2021 and the flood in Greece and Libya of September 2023. Again, some other example. This is the storm Boris that hit the Italy, northeast Italy, and the eastern part of Europe in September 2024. The Italian Civil Protection used the precipitation product to monitoring the evolution of the event, together with other satellite products. And in this example, on the right, we see the evolution of the soil moisture, and see that the products, the capture, well, of course, the event, so the anomaly of soil moisture is particularly positive in this area in East Europe after the event. Among the activity of the SAF, there is also the continuous validation, say, quite not day by day, but after the many important events. So also in this case, the consortium perform a comparison between the products and the radars in Hungary, for example. And we also use the precipitation products to estimate the evolution of the Mediterranean cyclones of 2023, September 2023, that caused extensive flooding, especially in Greece, Bulgaria, and Turkey, and then in Libya. This is analysis of the precipitation of this particular event. It was very severe in the coast of Libya. You see this yellow square here. The precipitation in that area was around 300 millimeters in a day, and it caused severe damages in the Dharma city. You see here a picture of Derma before the event and after the flooding. The flood effect were particularly severe because the precipitation caused a collapse of the dams that flooded the entire city. About the possible use of satellite soil moisture, these plots show the evolution of the soil moisture during the drought that hit Europe in 2022. This drought was particularly severe in Italy. You see in this picture on the right the anomalies of precipitation compared to the anomaly in temperature for several years. 2022 is this red dot, so we have a very positive anomalies in temperature and a very negative anomalies in precipitation. So it was very severe. In Italy, on the nationally monitoring table that involve several authorities, the anomalies of precipitation from satellite are used for estimate the severity of the event, and also the anomaly in soil moisture. One of the part of the Italy that was mostly affected by the drought was the northwest part of Italy. You see this small red dot here, and this is the evolution of the surface soil moisture from ASCAT with the climate, the observed climate. So you see the soil moisture in this area was particularly low. Another operational use, in this case of the snow products that we have, is within the hydrological national model. We have an hydrological model developed that cover whole Italy, that include also a cryosphere module. The name of the cryosphere module is S3M. So this model assimilate the snow cover estimation from HSAF and evaluate the snow water equivalent. So we see here the anomaly in the snow water equivalent for the 2022. It was particularly severe for all the Italian side of the Alps. And we can see here the evolution of the snow water equivalent for the 2022 year compared with the medium, the mean value for a short climatology that covers only 12 years, but it's quite significant that the condition were very low. And here we see also the evolution of the snow cover anomaly for the whole Europe in the 2022 using the snow cover area product H10 that we developed. You see that the red colors means a negative anomaly of snow cover, especially in east part of Europe, and you see also the Italian side of the Alps very red, so the conditions were very severe. So those products are used operationally for monitoring the evolution of the event and in terms of precipitation, but also for monitoring drought condition. If you are interested in knowing more about the HSAF product, we have an e-learning platform that is freely available. Information for the registration are available on the HSAF website. You see the link here. The module platform provides an introduction to the satellite products and it is available in English and French. And the product can be downloaded through different FTP server. They are also distributed to Helmetcast or the Puma station. And ASAP, they will be also easily downloadable from the HSAP website. Some of the products are also can also be viewed on the Helmet View, that is the web platform of HelmetSat. All those information are they are available on our website hsaf.meteoim.it. So that was an introduction to the product that we have and their how they are used in some practical application and on how they can be used in hydrology. Thank you.
Thanks, Simone. Very informative. It's very impressive to see the several products HSAF is providing for operational use. Unfortunately, we are so much behind the schedule, so I follow the same approach. And please ask in the chat. I'm sure there are questions to Simon. We have 3 presentations left for today. So there's Marcelo, San, and Matthias. When we are almost there at 3, I wanted to ask if any of you, 3 of you who are left, you have an urgent schedule, you need to leave, we need to go to the other meeting, etc. So we can take one of you now, or then we continue with Marcelo if you are all okay.
Well, I'm busy, so I need to leave at 30:30 at latest. So
okay,
preferably
so if Marcelo, if you're fine, we take Matthias now, and then we continue with Marcelo and Sean after that.
Problem.
So
No problem.
Matthias, floor is yours. Thank you so much.
Thank you. I'll just share my screen. I suppose you can see my slides.
Yes, it's good.
Well, in fact, this is actually, I think, a good place to talk after Simone's presentation because we share common things. So I will talk a bit more about the snow products in EUMETSAT Hydrosaf project. And The benefit of HydroSAF is that we are providing satellite products for operational hydrology, and they are freely available. And as Simon showed already, we have precipitation and soil moisture and snow products. So it's a kind of a complete package of multiple variables for hydrology. And snow is, of course, also critical for water resources, flood forecasting, drought prediction, and climate studies. And also the HydroSAF products, some of them are tailored for numeric weather prediction. And of course, the challenge with the snow products is that, well, of course, every satellite product, but we aimed for high resolution data and also timely snow information and try to reduce the errors. And I would say one of the benefits of the HydroSAF project is that there's, as Simone already mentioned, that there's we have a validation, hydro validation cluster, so the products are validated every second year, and also we compare the results with the hydrological models. So I would say the HydroSAF is a kind of a complete package for this purpose. We have also, it was mentioned in the previous presentation that we have plenty of there's always a different product. Sorry. Many products with different instruments, so the sheer amount of the products could be kind of it doesn't maybe show clearly what snow parameters that we are monitoring. So I would say the parameters that we are providing are snow extent, so it's on binary snow mask, so if there's snow or not. Fractional snow cover, we have we describe the fraction of snow in that pixel. Then the snow water equivalent, that could be maybe the most important parameter for hydrology because it tells how much snow mass you have in a certain region. And then we also provide a wet dry snow status product. Quite many of the products are based on visual or infrared satellite data, but we also use microwave satellite observations. And the main SWE products are they are data fusion of synoptic observations and spaceborne derived microwave derived SWE estimates. And quite many of the snow products are such that FMI provides the flat areas and TSMS provides the mountainous areas. Traditionally, or in the early phases of the project, our primary focus was on Europe, but we already have a global and hemispherical products as well. For the validation, I would say also the target validation areas are Nordic regions or Finland. So we have a homogeneous winter snow and quite dense validation networks. And then for mountains, the main validation area is in Turkey, the mountainous test areas. But we also have in the project data from Central Europe, like Germany and Slovakia. And in addition of validating against in situ data, we also do intercomparison with a satellite, other satellite-based products such as ODIS, Landsat, and Sentinel-2. Here I just present a quick summary of the products. So as you see, the product codes are quite uninformative in a way. But you can see here basically that as I mentioned before, the parameters are snow extent, fractional snow cover, wet and dry snow status, and snow water equivalent. And there are plenty of different instruments that we are applying. And I guess maybe the latest operational product that we have is the H43, which is also a snow extent product, but it's based on the MTG satellite FCI instrument. So it's maybe interesting in that respect. So and it's a geostationary satellite disk that we provide the data in. Unfortunately, this image is not maybe that illustrative because I guess this is from the early stages of the product development, and unfortunately the data we had didn't have much snow. The dates were actually bad for that purpose. But anyway, you can get a kind of idea what the product looks like, or the quick look looks like. Then, of course, we are also doing hydrology at FMI. This is my colleague Jaakko Ikonen, who is mostly involved in this, and he has been developing an in-house hydrological model, HOPS, and we are applying those models to the Kemijoki River basin in northern Finland. It's mostly north of the Arctic Circle, so it's very up in the north. The area is pretty large, so it's actually slightly larger than Slovakia, and the temperatures are Arctic temperatures. And one of the challenges for optical-based snow products is that during winter, when we have snow, it's polar night, so there's no daylight, or the days are very short. So getting the snow information is not that straightforward. This region is quite flat. There are plenty of lakes and plenty of peat bogs. And the actual Kemijoki River it has two branches, western and eastern branch. And there are actually quite many hydropower plants in that region. So there are 16 power plants in that region. So it's 1,100 megawatts production. So it's about 30% of the national hydropower production, basically. And the main season is, of course, during spring, when the snow starts to melt. So in practice, if we know how much snow we have in that region, then that could help planning the hydropower production. And well, the snowpack aerial volume is, we need to know that. So basically, we can get that information from the snow water equivalent, but also the snow melt rate and timing is quite crucial. Maybe you noticed that we didn't have such a product in the portfolio, so maybe there's a room for improvement over there. Jaakko has been using the Earth observation-based snow products, fractional snow cover, and also the SWE. For the SWE, well, the optical data, as I mentioned, it's not only the polar night that's maybe complicates things, but there are also the question of clouds. So it has more role of visual verification rather than using, or it's not used as operationally in that respect. The SWE product is a quite low resolution, but it does give you an idea of the amount of the snow in the region, in particular when we are talking about quite large area. And it's easy to assimilate into hydrological model. I would say the main disadvantage is that the snowmelt, during snowmelt, the sweep product is less reliable. Or I would say the maybe around the peak snow in the maybe around January, February, or late February, the product gives the best results. But then when the snow actually starts to melt, then the product becomes a bit more unreliable, in particular in respect to the timing. So the wet snow actually makes things harder to estimate, even though we are using data fusion here. Yeah, and we are also doing some aerial coverage of the region. The way Jaakko has integrated the HydroSAP SWE data to the his in-house model is that it's kind of a snowfall correction performed for every grid cell. So there are, as you see, there are quite many different rules that he has been using. So he adjusts the hydrological model in respect these rules. And since you cannot get the snow melt from the any products, he uses the model to estimate that. And again, like maybe during the you can get the from the SWE product, you can get the peak snow pretty reliably. But when the melt season starts, then there are issues. It's not that reliable anymore. And this type of assimilation to hydrological model, it only affects the discharge volume. So here are some of his results. So you could argue that when you integrate the SWE values to the model, there is improvement, but it's sometimes it's just a slight improvement. And again, these results actually show that sometimes also the satellite data product cannot catch even not the peaks SWE totally reliably, because if there's a huge amount of snow and the snowpack is very thick, then also the saturation of the signal affects the product. So sometimes this is not also captured that well, but I would say the general result from the integrating the HydroSAP SWE to our in-house hydrological model is that it does improve the hydrological forecasting. So this was basically my presentation today. So I don't know if there's a time for any quick question. I doubt that, but I can spend maybe 10 minutes online yet. So if there are any questions in the chat, I can respond those.
Thank you so much, Matthias. This was very interesting, and it's indeed it was very good to have this after Simone's presentation. And it's also important to see that in some countries, indeed, snow is the main thing and very important. And it was great to see the overview of the HSAF products for snow. So thanks a lot for you. Indeed, let's have questions in the chat for Matthias. I appreciate if you can follow a bit. And also, my greetings to Jaakko. I used to work with him, so thanks. Let's move on.
Okay, I will tell you greetings.
Thanks. So, and the next presentation is by Marcelo Uriburu, and you will present about the hydrological applications in South America. So over to you.
Exactly. Thank you. Thank you very much. I will share my screen. Hold on.
Yeah, Marcelo, please let me know if you need support. Okay, yeah, it's coming. It's good.
No, I think, can you see it well?
Yes, it's good.
Okay, there we go. Like this. Okay, thank you very much. I'm Marcelo Uriburu Kirno from the Earth Observation Division in CONAE, the National Space Agency of Argentina. You only see my name there because I prepared the presentation, but of course there's a whole team behind the products I'm going to present. So my presentation is structured in this way. I will show some satellite precipitation derived.
Can you put your mic a little bit closer to your mouth? I think it's
sorry, any better?
Great. Thank you so much.
Okay, sorry about that. And a second part on satellite soil moisture derived products. So first of all, I'm going to deal with the GPM iMerge based antecedent precipitation index. As a reminder, maybe this is an index very well known for most of you. This is a proxy of the soil moisture. It's basically computed with precipitation, in this case provided by iMerge products. It's a very simple model, order one autoregressive model, as you see there in the screen. And if you see how it plots, you see upside down the rainfall bars, and then you see the evolution of this index, the antecedent precipitation index, that it behaves very similarly to the soil moisture. I mean, it shows abrupt jumps when it rains, and then you have an exponential decrease of the value. So basically what we have here is the gridded precipitation from the GPM mission, and then just a very simple processing of it, and we get the gridded API. So we have this proxy of soil moisture, and we are computing that on the southern South America region. So based on that product, what we can do also is to compute the percentiles. The good thing here is that we have more than roughly 25 years of record in iMerge, so we have a good reference period for computing percentiles of the API. In this case, we do it on a weekly basis. And then what we get here is an indicator of the catchment status, the hydrological status. Of course, it represents the antecedent condition, that is the prevailing readiness of the soil to generate runoff in case of a storm. It's also interesting to mention that in this way, computing percentiles, in a way, you remove the biases that are present in iMerge precipitation estimates. Also from the API, we are computing just in this Pampas region in Argentina, which is the richest area, the core area in agricultural terms. We compute the very well-known curve number, which is basically based on soil characteristics and land cover characteristics, but it's usually modulated by the recent rainfall. In this case, we do like a softer modulation with the API as a proxy of the soil moisture. Basically, this is a very well-known method to compute based on a precipitation, to compute the portion of it that will become runoff, and then you can convert that to hydrograph if necessary. This is the formula you use for going from API to the value of the CN. Another one, which is in the limit of hydrology, but it's a rainfall triggered shallow landslides. This is a very recent product we are developing. We are applying it just in one basin in Argentina based on requirements of some users in that area. The underlying model is a very well-known Moore-Coulomb model for shallow landslides. But the interesting thing here, I think it's run in prediction mode, because we are crossing the susceptibility to for landslides with the soil moisture condition as computed from the API. But the thing is, we progress the API into a forecast horizon of roughly 3 days, computing the API based on QPF provided by the GFS numerical weather prediction model from NOAA. So it's got a daily step. The issuance frequency is 1 every 3 days with a lead time of 3 days as well. And we propose different failure planes at different depths. In this case, it's 25, 50, 75, and 100 centimeters. And the pixel size is 30 meters. It's imposed by the digital elevation model that's behind this. So what you have at the right of the screen, on the right of the screen, is the classes we are getting from this application. I'm not going to go into much detail here, but what you have on the left side is this scheme shows the pixel by pixel. What you have is depending on the ratio of the slope and the tangent of the internal friction angle of the soil, depending on the value of the prevailing API today or in the following days, as I said, you fall within different categories. You have the unconditionally unstable areas, which basically do not depend on the soil moisture. The same for the unconditionally unstable to the right. But then you have an intermediate area in which, depending on the value of the API, you can have a stability condition. The pixels are stable under the prevailing soil moisture, as it says there. And if you have higher values of the antecedent precipitation index, you can have a low instability or high instability depending on those values of the API. Of course, there's some calibration or adjustment of this model. You have to define the thresholds of the API based on observed events. Maybe this sounds familiar to some of you because this is inspired on a model that proposed Dalia Kirschbaum from NASA. There are some differences in the way I use the API, but the philosophy or the rationale is roughly the same. With respect to satellite soil moisture derived products, first of all, I want to show the estimates we do using the SAOCOM-1 mission. It's a constellation of two L-band SAR satellites of Argentina. And this, again, this estimates of surface soil moisture is computed again in the Pampas region, but we are progressing to cover the whole country. It's not regional, unfortunately. The model we used has been developed at the Tor Vergata University in Rome and in conjunction with CONAE. It's a direct backscatter model that relates the backscatter with different variables, some of them depending on the sensor, like the wavelength and partially the local incidence angle, but the other independent variables depend on the target. But basically what you see there is that one of the independent variables is the permittivity, which is also a function of the soil moisture content. So that's basically the challenge here is the inversion of this algorithm. You have to use quite sophisticated numerical methods like data cubes, etc. This is a surface soil moisture. It's nominally it's 5 centimeters. Nobody knows exactly how deep it goes, but it also depends on the soil moisture content. But that's roughly the depth of the estimate. But based on that, what we also do is for the same Pampas region is to compute the root zone soil moisture, or basically down to 50 centimeters. This is not always the root zone, but it's a soil profile average. In this case, and I mentioned this earlier today, what we do is it's combined in a SVAT model. In this case, is the DSAT CSN version 4. It's a soil vegetation atmosphere transfer model, plus the assimilation of the Southcombe surface soil moisture. That's usually done with the ensemble Kalman filtering. Down there, you have the link if you want to visit the geo portal where these and other products are shared in CONAE. Based also on this root zone soil moisture, we also compute just for a number of basins within this core area in Argentina, what we call the flood guidance. This is inspired again on the very well-known flash flood guidance. The main difference here is that our lead times are of 1 and 2 days. We cannot afford to go down to lead times of less than 6 hours as the flash flood guidance presents. But basically, what we have here is a product that, in a way, it computes a threshold, a rainfall threshold that is sufficient to cause a bankful flow at the basin outlet. That depends on the catchment characteristics, of course, but also it highly depends on the soil moisture content. And I think that's my last slide. Also, based on the root zone soil moisture, we have developed this this product. It's more on the agrohydrology sector, focused on the agricultural sector. It allows you to make estimates on crop yield. Basically, what we have after using this model is different scenarios of yield, in which you can modify or play with the sowing dates or the dates and dosage of fertilizers and agrochemicals. So you get different estimates of yield for different crops. I showed here an example on maize, but of course we have that for soybeans, which is probably our most important crop nowadays, and some others, some other crops. And what we have here, well, again, we have the link down there in case you want to visit it. And this is it. Back to you. Let me share the screen.
Thank you so much, Marcelo. Very interesting, and thanks for reminding us that hydrology links to indeed also other applications, not only flooding, also agriculture, etc. So that's great. Again, unfortunately, we need to follow the same approach. So please, any questions to Marcelo, put them in the chat. And we follow with the last presentation by Sean, who is presenting the satellite-based hydrological applications in North America. So floor is yours.
Yes, can you see my slides?
Yeah, we can see them well.
Okay.
Thanks.
So thank you very much for the time to be able to cover. Let me put
Sorry,
in presentation mode.
Can you make a presentation mode, please? Yeah.
So thank you very much for the opportunity to be able to talk about North American hydrologic applications from satellites. Here's an outline of the presentation. It's going to cover some of the NOAA applications and use cases, and then we're going to cover the USGS, and then a few applications from our Canadian colleagues. So I'm going to take you through do it a little bit different than some of the others have done, and take you through the value chain in a maybe a different perspective. it all starts with satellite observations, and NOAA gets in various satellite platforms, some of which are listed there over on the left, and then make satellite products from this, which is where a lot of the talks have really focused on, is how do we create radiances, visible imagery, precipitation products. But I'm going to take you a little bit further down, and most of my talk is going to be talking about those NOAA models, services, and products, and to be able to kind of show you a little further down in the value chain how the satellite products are actually used by forecasters, as well as some of the things that are done with them for decision makers and users of the forecasts. You can go back certainly in your own time and look at this non-exhaustive list of types of products that NOAA winds up creating, some of which I'll highlight here. Just a quick overview of the National Weather Service's hydrologic program. There is a National Water Center, which is the headquarters, basically, of located in Tuscaloosa, Alabama. They do most of the river modeling, as well as a lot of the remote sensing applications from that national center. But it's also 13 river forecast centers located throughout the country. You can see some of which, of course, the basins extend into Canada. So we work closely with our Canadian partners to make sure we have the best estimates. And then at each one of the basin areas or forecast centers, there's also these national forecast offices with 122 of them located throughout the country. Before I guess moving on here, I just wanted to put the idea of information decision support services, which is where the National Weather Service here in the U.S. is going, changing a little bit of its focus area from just producing forecasts to actually helping users to apply those forecast data for decision making, and that's some of that value chain that I was discussing earlier. As has been discussed by various talks, the remote sensing data can wind up going into a lot of these modeling applications. For NOAA, that includes weather, hydrologic, climate, and ocean models. They are ingesting all forms of data. It's kind of forming the backbone of the observational profile going into these fundamental models that help to provide all the guidance that forecasters wind up applying. It's used, as was discussed by our first talk of the day. Luigi discussed how it's used for verification, calibration, and assimilation. But from there, the data actually goes in one of two ways. One, it can wind up going down to the model output, can wind up going to the weather forecasters. And at the nowcasting brief from that was presented by Brian Gockel, I think it was 2 months ago at this point, he really covered AWIPS ad nauseum as to the forecasting. This is the forecasting display environment. It's actually unified throughout the entire country so that all of the groups or the forecasters are working on this consistent network of workstations, although they may have different data flows as to which data they're using to apply based on their region. Those weather forecasters also wind up applying the remote sensing data along with the model output in order to be able to construct the forecasts. Secondly, there's also the river forecasters. We're taking what the weather forecasters apply, what the models are giving them from things like the National Water Model, as well as the remote sensing data and they typically use a GIS environment as their integration tool for all this data to try and come up with an estimate for river forecasting conditions. So if we look at some of the end product of this, one of the things that's being developed at the National Water Center is within the National Water Model is flood mapping. So the flood inundation maps that they're generating all start with remote sensing data and then apply that through hydrologic models in order to be able to come up with where they believe overall extent is going to wind up happening for floods. And of course, this can be used in real time as well as in forecast mode. This is an example of one of the flood products that was generated. So it can give a much more tactical information as to where assets need to be applied, where we think floods are going to wind up occurring, and how those decision support capabilities can be deployed. Here's an example that from one of the forecast offices of how they used the GOES 16 images to be able to help take what the model forecasts were doing and maybe have to be able to make adjustments to it. So while model forecasts were still continuing for water to continue down the Colorado Basin, that's not where the water ended up going. And they actually were looking at this in real time using the GOES imagery to be able to see that the water was starting to be able to make its way over into a completely different basin. Basically, once it reached the surface height, it started to be able to migrate across the plain, these very flat areas, from one basin to another. So the Colorado River was basically pouring into the St. Bernard. It was basically through the use of GOES imagery that the forecaster was able to alert the local officials downstream in as quick as possible to be able to make this adjustment that models were not picking up, but the forecaster was able to see from using satellite imagery. Going to the areas of Alaska now to show some of the complexities of their system. They not only have to be able to deal with the flooding conditions that are caused by heavy rains, but they also have lots of snow. They have ice conditions, ice jams that wind up occurring, with ice jams actually making up the majority of the disaster declarations for the state. Some of the some of the data once again goes into this the operational hydrologic model, and this CHIPS model is actually all throughout the country, but in this case for Alaska, this is just showing you some of the satellite assets that wind up going into it, from precipitation to clouds, vegetation. And then it's calibrated against the 30-year historical data. This is, once again, somewhat routine across the board. But this is also winds up using surface observations to help relate or add some reality to the hydrologic model input beyond what the satellites are fully capable of doing, to make sure that those forecasts can be as accurate as possible. Here's also a satellite-derived product from using VIIRS that shows the aerial coverage of flooding. This was actually from the May 22 flood along the Yukon River. Very challenging area to be able to try and forecast, because those white areas that you see there, that's the snow. Basically, this is a snow melt driven event along with ice jams. So the water just backs up behind the ice jam after the snow or during the snow melt all along the basin. And this caused evacuations throughout Galena and several other towns in the area. Especially during a time during COVID, which made its own challenges to be able to execute an evacuation of these towns. I invite you to go over. There's a link provided to some of the flood products. There's not just this VIIRS product, which is 375 meter on there, but there's also some other SAR-based flood products, as well as a downscale product that I'll demonstrate right now. So another flood example was during the glacial event of the Mendenhall Glacier, which tends to it's going through a melt stage, and as it continues to be able to pour into a lake, it will generally, there's always a threat, I guess, of it overflowing, particularly every couple of years. But in this case, the VIIRS, it does not really have the resolution to provide where the flooding is occurring. So NOAA has actually developed a downscaling version of this product that once again uses hydrologic modeling in order to be able to better estimate where the flood depth is within areas. And this product was able to really kind of hone in on those locations as that were under threat during this flood event. There's also the application of synthetic aperture radar, as I spoke about, not only for, in this case, monitoring river ice jams that are, of course, important not only in Alaska, but places like the Red River of the North that's located in the central areas of the United States and Canada that have routine threat of flooding nearly every year. So the rivers constantly need to be monitored for when this river and lake ice is going to be breaking up. And then lastly, we are also doing some monitoring of floods. A lot of this is in test mode, I'll say, or experimental stages to be able to come up with the best way to not only monitor flood conditions using SAR, which can give you high resolution, cloud-free estimates of flood extent, but can also wind up, but does have its limits as far as understanding what's happening underneath the canopy. So it certainly is not without its challenges. The U.S. Geological Survey also winds up using various satellites for their estimates. They do, it's kind of broken up into, I'll say, 3 areas. One is water quality, which they do, as it said there, they mainly use their Landsat instruments for doing this kind of water quality estimates for water temperature, chlorophyll. It's really understanding how healthy those aquatic systems are, but then also water quantity, where they're measuring evapotranspiration, water levels, water discharge, all along the water areas, river areas throughout the United States. And the third area I'll post later is with FuseNet, which is not really just about monitoring over the United States or North America in general. It's actually something that's not measured over U.S. or Canada at all, but it's mostly a measure of drought severity and famine, potential for famine monitoring, and that's actually done across collaboration throughout the U.S. government. Moving into Canada, you could start to see some themes popping up here. This is actually a contribution from the Yukon province that was showing how they also are monitoring river ice and along the Yukon on the Canadian side of the boundary. The strength that the Canadians have is by having the RadarSat Constellation mission, they can actually task multiple collections per day over the exact same area, which really helps to be able to monitor how conditions are evolving on a very consistent basis. They also use Sentinel-2, which of course is ESA's instrument for their real-time monitoring of the ice and flood conditions. And lastly, I just wanted to cover how the Canadians produce the snow mass from remotely sensed data. Number one, it really starts with those MET forecasts, which are, and precipitation analysis, which are really modeled estimates derived by other satellite data. But then it's fed into a snowpack model, a one-dimensional snowpack model, and then further constrained using the interactive multi-sensor and snow and ice mapping system that NOAA produces for to help constrain the overall extent of where the snow is occurring. And it's fed into the Canadian land data assimilation system to produce what you're seeing on the right, which is a 2-kilometer snow depth. But that the future is very bright for being able to make this product much, much better. Number one, they're replacing or updating the land surface scheme to make it much more complicated. It's a multi-layered snowpack model compared to the one-dimensional. Number two, this is going to be a big change in that not only using the IMS, but they're looking to be able to apply AMSR 3 and AMSR 2 as part for passive microwave, as well as the upcoming SIMMER mission from ESA. But the big one is the terrestrial snow mapping mission, which is actually going to be a dual Ku band instrument that the Canadian Space Agency is looking to launch, that I will say is pretty much just a game changer in being able to measure snow, because all of the other ones, other types of instruments, are not really designed for measuring snow. They don't really have the kind of capacity for being able to measure deep snow depth. But this mission is actually working in frequencies that will change all of that. And then lastly, they're going to be doing some updates to the land simulation system. I want to thank all my fellow contributors and for you listening today. Thank you.
Thank you, Sean, very much for the great, very complete presentation on the operational services in North America. I think we can take questions now because we are soon closing the meeting. So chat is not very useful then. So if there are any questions to Sean, now it's your turn. No questions? Okay, maybe there will be. Sean still monitor the chat. So thanks a lot again for your presentation. So now we are end of today's presentations. I think it was great set of applications in the different regions, and what I see there, I think we are pretty well covered what we have proposed to be as a core measurements in our table. So there are many things there which are very well resonating of the presentations today, especially for the land parameters. As you see, they are in many presentations. They are highlighted, and the importance of that. And I think we are also covering those pretty well in our Excel sheet. So I thank you a lot. Lihang, you have a final word for the day.
Thank you. Just want to thank all the presenters and all the attendees. Great presentations, and I would encourage everyone to probably prepare the answer of the 5 questions and identify any of the update of the table and bring it to the tomorrow breakout sessions. Thank you, and really enjoy the presentation. See you tomorrow.
Thank you. Joining you then tomorrow, and indeed, as Lihang reminded, you can think about the questions already a little bit and prepare yourself to be active in the breakout session then tomorrow. So thanks a lot. I think we can close. Zoya, did we forget anything, or do you have anything to add?
No, we are good. Thank you.
Okay, thank you, Zoya. Thank you, everyone. See you tomorrow then. Thank you. Bye-bye.
Bye, thank you.
Thanks, everyone. Bye.
Bye-bye. Thank you. See you tomorrow.
Bye.